So in this video, I just want to quickly talk about how we can estimate the size of atoms or ions using the periodic table, at least the trends in the sizes in it of the atoms and ions. So remember, if this is my periodic table, there's a quick cartoonish graph of the periodic table, there are two key trends. One, size increases as you move down a group, and it decreases as you move right across a period. The size increasing as you move down effect is coming from the principal quantum number. As we start filling more and more shells of orbitals, as n, the principal quantum number, gets larger, we find that these orbitals tend to extend further from the nucleus. So the orbitals are generally getting larger, the atoms are getting larger. So that's why trend 1 is true. Trend 2 is true because of the z effective that we talked about in the primary lecture. Z effective is generally increasing as we move to the right. That is, the effective nuclear charge is increasing as we move to the right. And you can again see the original lecture for details of why that's so. But the main factor then is that the electrons are being pulled more tightly by that larger effective nuclear charge as we move across the right. Therefore, the general trend is that we have the largest elements in the bottom left, and we have the smallest in the top right. And so again, down increases size, right shrinks size. And so using this, you can go ahead and try to do some examples where we try to estimate the relative sizes. So for example, if we take oxygen, silicon, and sulfur, and you can look at the elements in the periodic table right here, what you see is that oxygen and sulfur are in the same group. So actually, let me back up. The strategy here for ranking the size of these, we're going to rank these from smallest to largest. The strategy should be that we're going to look for pairs that we can determine readily, and then based on those pairs, put everything together to get an overall trend. So first off, looking at the periodic table, I see that oxygen and sulfur are in the same period. Excuse me, the same group, with oxygen being in the earlier period compared to sulfur. And so we know that sulfur is going to be greater than oxygen since sulfur is below oxygen in the table, in the same group. Second, silicon and sulfur are in the same period, but silicon is further to the left in the period. And so it's going to be larger. So we know that sulfur is less than silicon because they're the same period, and silicon is further left. So it's going to have a smaller z effective. So I can combine these two then to see overall that oxygen is smaller than sulfur, which is smaller than silicon. Then when it comes to ions, these same basic ideas apply, and then there's the extra two wrinkles of, well, one, when you take electrons away to form a cation, you make the atom smaller because you have the same positive charge in the nucleus, but less electron-electron repulsion because you have fewer electrons, so those electrons get pulled more tightly towards the nucleus, and the atom size shrinks for a cation. For an anion, it's the opposite effect. I now have an extra electron. There's going to be more electron-electron repulsion. It's going to cause my atom to expand its electron cloud, and therefore anions are larger than their parent atoms. And of course, anions you rarely get more than 1 or 2 electrons, but for cations you can often take away several electrons, and the more you take away, the more it's going to shrink, or the more you add in the anion, the larger that anion is going to be.